through the topics from Module 10 in order to get ready for the Module 10 quiz. So problem 1 asks us to list the sample space for flipping a coin, then rolling a die. And we're typically going to be talking about a 6-sided die. So my sample space is S equals with the curly brackets. Now, I can't list them as separate events because I'm doing them together. I'm flipping a coin, then I'm rolling a die. So the first outcome is that I could land on heads with the coin and roll a 1 on the die. So you have to work that way through every number for the flipping a coin and landing on heads. So then we can have heads 2, H3, H4, H5, H6. Then I have to do the same thing for working my way through tails and all of the outcomes on the die. So tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. So those are all of the possible outcomes for if we flip a coin and then roll a die. So question 2 says, in the example above, what is the probability of flipping a head and rolling an odd number? So what we need to do is we need to find all of the outcomes for heads that had an odd number. So that's H1, heads 1, that's odd, heads 3 is odd, and heads and 5 is odd. So that means my probability there, 3 of my outcomes were flipping a head and rolling an odd number over my total number of outcomes, which there are 12 of them. So 3 out of 12 can then simplify to 1 over 4. All right, so for number 3, we have that we're rolling a die and then we're spinning our spinner with the letters A through H. We want to list the sample space. So very similar to number 1 with our sample space, we have to do a combination. So I have to go through all of the numbers on the die, and they each also have to get all of my letters. So that means 1A, 1B, 1C, 1D, 1E, 1F, 1G, 1H. So I have to go through this for every number and all of the letters. So then 2A, 2B, C, so it is going to take just a little bit of time to go through and write all of the outcomes. All right, so we listed 1A through H, and the same thing for 2 through 6. So there are a lot of possible outcomes. Question 4 asks us for the probability of an even number and a vowel. So if we go through all of our even numbers, so we have 2A, 2E, and that's this. We also have 4A and 4E, and we have 6A and 6E. Those are all even numbers and a vowel. We then need to know how many total outcomes there are in our sample space. So if you count up all of the outcomes, there are 48 elements because there are 6 numbers and 8 letters. So I multiply this together and I get my total amount. So my probability, if I count my number of outcomes, I have 6 out of the total 48. And when we simplify 6 over 48, we divide both of them by 6, we get 1 over 8. So there's a 1/8 chance that you can pick an even number and a vowel. Question 5 asks us the probability of an even number or a vowel. So this is a little bit different. So first we have to count all of the outcomes that involve an even number only. So that's 2 through H, 4A through H, and then 6A through H. So we count all of those and we get 24 out of 48. We then go through and count all of the outcomes that contain a vowel. So 1A, 1E, all through all 6 numbers. So there are 12 of those out of 48. Okay. Now, because these are not mutually exclusive events, you can have an even number and a vowel. We then have to subtract the overlap, which we just calculated at number 4. We know there are 6 elements out of the 48 that are an even number and a vowel. So when we do 24 plus 12 minus 6, we're going to end up with 30 out of our 48, which when we simplify gives us 5/8. So there's a very good chance that if you roll a die and then spin the spinner, you're going to get either an even number or a vowel as your answer. Lastly, on number 6, we want to find the probability of getting not an 6 and not an H. So that means 1A through G, because those involve not 6 and H. Same thing for 2A through 2F. I work 3, 4, and 5 work the same way. And then I can't have any of my outcomes that contain 6. So if we go ahead and count all of those up, we get 35 over 48. And that cannot simplify, so that is our final answer. So number 7 says if the probability of A is 0.2 and the probability of B is 0.3 and the probability of A or B is 0.4, are A and B mutually exclusive? So in order to determine if these are mutually exclusive, I want to know if the probability of A plus the probability of B equals the probability of A or B. So basically, does 0.2 plus 0.3 equal 0.4? So if I add my probabilities together, 0.2 plus 0.3 is going to be 0.5, which does not equal 0.4. So in this case, they are not mutually exclusive. So for 8 through 10, we're going to use a coin is tossed and a single card is drawn from a deck of cards. Find the following. So 8 asks us for the sample space, and I'm actually not going to write out the entire sample space because it would take a very long time since there are 52 cards in a deck, and I'm not going to write all of the outcomes. So I'm just going to write some of the sample space. So I can flip a coin and get a heads, and then I could draw an ace of hearts. I could flip the coin and get heads and draw the 2 of hearts. Flip the coin and get a heads and the 3 of hearts, and I would work my way through all heads and all hearts, clubs, spades, and diamonds. Then I would do the same thing for tails. And if I listed all of those, there would be 104 elements. So 104 things is a very large amount to write out, which is why I'm not writing them all out, because 104 elements would take a very long time to write out. So 9 asks the probability of tossing a heads and drawing a diamond. So because there are 52 cards in the deck, and 52 of my outcomes are going to contain heads, because I have to go through heads and then all of those cards. And then there are only 13 diamonds in a deck. So I'm going to have 13 of my cards that involve having the heads in front and then all of the diamonds out of my total 104 elements, which we then simplify to be 1/8. 10, we want to know the probability of tossing a heads or drawing a diamond. So I already talked about the fact that 52 of the outcomes contain the flipping head, so 52 out of 104. For drawing a diamond, there are 13 diamonds that correspond with flipping a head. There are also 13 diamonds that correspond when you flip tails, so that means there are 26 total outcomes that contain diamonds. And then we want to subtract the overlap. So that's the probability of tossing a head and drawing a diamond. So there are 13 out of 104. So when we do 52 plus 26 and then minus 13, we're going to get 65 over 104, which then simplifies to 5/8. So again, a very good chance that if I toss a coin and then draw a card from a deck, one of them will be heads or a diamond, potentially both. Okay. And then on number 11, we want to know the probability of tossing a heads given a diamond was drawn. So I'm going to label tossing a head as A and drawing a diamond as B. So the probability of A given B equals the probability of A and B over the probability of just B. So it's always the probability of both over the probability of whatever the second thing is. So we've already calculated the probability of tossing a head and drawing a diamond. That was 13 out of 104. Okay. We then also know the probability of just B, which is the probability of drawing a diamond. We calculated to be 26 over 104. So we're dividing two fractions with the same denominator. Anytime we divide two fractions with the same denominator, we can get rid of them. So this basically becomes 13 over 26. And 13 over 26 becomes 1/2. So you have a 50% chance of tossing a head when you flip a coin, given you already drew a diamond. All right, so for number 12, we're gonna use our table to answer the question. So we wanna know, are the events excited and Olentangy mutually exclusive? So remember, mutually exclusive says they can't happen at the same time. So I just have to look to see if I have any excited students who are also from Olentangy, and we do. So the answer is no, because a student can be both excited about college and from Olentangy. So 13 asks us the probability a student is from Olentangy or excited. So because we've already discussed the fact that these are not mutually exclusive events, I'm going to have to subtract the overlap. So the first thing I want to find is the probability a student is from Olentangy. So we look at the total number of students from Olentangy and we put it over the total number of students we have. So we have 350 over 1,000 plus, then we want to add the total of number of students who are excited about college, so that's 450, and put it over our total, which is 1,000 still. Then we want to subtract the overlap. So that's the box where we have our number of students who are from Olentangy and excited from college, which is 150 out of 1,000. So when we do 350 plus 450 minus 150, we're going to get 650 over 1,000. And if we take the fraction 650 over 1,000 and simplify it, we're going to get 13 over 20. Next, we want to find the probability a student is from Olentangy given they're excited about college. So again, if we let Olentangy be A and excited about college be B, we want to find the probability of both. So that's 150 over, we're dealing with a table. We don't actually have to write it as a fraction. So I have 150 students who are both from Olentangy and excited. And I'm going to put that over the total of a student being excited about college, which is 450. So when we simplify 150 over 450, we're going to get 1/3. I also want to do an extra example where we find the probability of a student being excited about college given they're from Olentangy. I want to show you that the order that we do the givens does matter. So now the probability of a student being excited about college is A, and the Olentangy is our B. So our numerator doesn't change. We're still doing the probability of the student being excited and from Olentangy, which is still 150. What changes is our denominator. So because our second thing is now Olentangy, I'm going to put the 150 over the total number of students from Olentangy, which is 350. So now 150 over 350 simplifies to give us 3/7. So the solutions are different based on what comes after the given bar, because that determines what total we're going to look at. So in case you see something like this on the quiz, make sure you pay attention to whatever that second word is, because that's going to determine the total row or column that you're going to look at. So our last problem says if A and B are independent and the probability of A and B is 0.16 and the probability of A is 0.2, what is the probability of B? So because the events are independent, the probability of A and B is found by multiplying the probability of A by the probability of B. Okay. We now know the probability of A and B is 0.16. We know the probability of A is 0.2. We don't know the probability of B. I can think of the probability of B as my variable. So if I had the equation 0.16 equals 0.2x and I wanted to solve for x, I would divide by 0.2 on both sides. It works the same way here. I'm going to divide both sides by 0.2. So 0.16 divided by 0.2 is going to tell me that the probability of B equals 0.8. Make sure that while you're taking the Module 10 quiz, you have that Desmos Scientific Calculator open in another window so you can use it on the quiz. Remember, the link is on the classwork page of Classroom. At the very top, it's named Desmos Scientific Calculator. If there's anything you have questions over, please make sure you contact me so I can go over them with you before you take the quiz.